Here we go, exercise 7A, basic counting methods. We're going to start off with basic counting methods. Tree diagrams. We're going to use, when we first start off the exercise, it's going to be straightforward. It's when you start using the formulas for permutations, combinations, where it might get tricky. Examples of that would be something like, there's a classic example of handshakes, and I think you might have heard of it from networks. Like, if I were to shake Jamie's hand right now, it's just two people, it's one handshake, right? If I then had Michael, I now have three people, I have 1, 2, that's 2 handshakes with me, but then Michael has a handshake with Jamie as well. So that's a total of 3 handshakes, yeah? Because he's shook hands with me, and I've shook hands with Jamie. The only person who hasn't shook hands is Michael and Jamie. So now 3 people makes 3. Now it gets more interesting when you get to 4. I will now have Jamie, Michael, and Rose. There'll be 3 handshakes. But then Michael hasn't shook hands with Rose, and neither has he done Jamie. So he now has to do another 2. So that's a total of 5. So we're counting. So 3 plus another 2. But then Jamie also has another Rose. Okay, so that means now that's a total of 6. Okay, so now if you think about the pattern, as I increase, if I said there were 20 people, how many handshakes are there? So now it's still counting. It gets tricky on how we work that out. And that's the technique. That's why I don't like this topic. I'm still trying to get my head around it. But to start off with exercise 7A, 7B, it's going to be really easy. We're just going to count things that are logical. We're going to use certain diagrams or tools to help us count. Because what we don't want to do is we don't want to sit there and draw out every handshake and every person that takes them. There has to be a way, there has to be a method to do that. So let's start off with basic counting methods. Tree diagrams. Most of these combinations you can draw it out. It's when it gets too complicated, like the one I just said, then drawing becomes an issue, that we have to find better ways. But to start off with, we can find out solutions by drawing them out. And so an example here would be, a restaurant has a fixed menu, so set menu, offering a choice of fish or beef. Okay, so you've got only 2 choices there, so you either choose fish or beef as your main meal. And then after you choose your main meal, then now you have a choice of cake, pudding, or ice cream for dessert. Okay, so you have a main meal, you have dessert. And the main meal has 2 choices, and your dessert has 3. So what's my total number of combinations? A combination example would be choosing a fish and cake. So that's one combination. I could choose fish and pudding. I can choose fish and ice cream. I can choose beef and cake. I can choose beef and pudding, and technically I've just almost named all the combinations. But you just said the answer, Ben? 6. So as a tree diagram, you can think of it as I can have fish or beef. Those are my only 2 options as a tree diagram. I'm doing a vertical tree diagram, or you can do a side tree diagram if you want. Fish, beef. Out of the main meals, after you choose one of them, then you now have 3 options. You have cake, pudding, or ice cream. And the same thing here, cake, pudding, or ice cream. And what you can see is for every 2 or every group, you get an extra 3. So that means you've got 2 groups of 3. You want to think about it. So 2 groups of 3 means 2 times 3. Which we can say 2 times 3 gives me a total of 6 combinations. Okay, so 6 different ways. So I can have fish and cake, fish and pudding, fish and ice cream. I can have beef and cake, beef and pudding, and beef and ice cream. Okay, so the technique that we're using today is called multiplication there. And it's just the idea of using logic. You've got 2 groups of 3. So we're saying 2 times 3 gives you a total of 6 ways. So instead of writing it out and listing it out, we can now figure it out, we can multiply the number of options we have. Does that make sense? Okay, so that's all we're doing. We're first starting off by counting. How do we count? We first figure out, well, how many choices do we have in the first go, and how many choices do we have in the third go, or second, or fourth, and we multiply them. Okay, so multiplying them, they give them a name. They call it the multiplication principle. Okay, but logically it makes sense. You're saying for every 2 you get 3, so you go like 2 groups of 3 makes 6. Yeah. So here we go. This is the rule or the principle. They say if there are n ways of performing one task, and then there are n ways of performing another task, then there are n times n ways of performing both tasks. Okay? And then that applies in not just by 2 tasks, it could be 3 or 4. So if I had a tree diagram where I said, in the morning you have a choice of choosing a top wear. So it could be a jumper and a singlet. Jumper, and then you have, after you choose your top wear, maybe you can choose your bottom wear. So you can choose now, I don't know, let's go with jeans, skirt, or trackies. So you got another 3. Then after those 3, maybe after you choose your bottom wear, you can choose your shoes. Maybe you have formal shoes. You have, I don't know, sneakers. Right? And then for every 2, maybe let's say you choose a particular sock that chooses with it. And you have 3 colored socks. You have, or 4 colored socks. You have black, green, yellow, and white. Okay? But the number of options and combinations what you don't want to do is list all this out. It takes too long. By the multiplication principle, you can figure it out and say, for every 2, there's 3, so 2 times 3 gives me 6. For every one of these 3, I get another 2. So that means 3 groups of the 2. So 2 groups of the 3, or 2 groups of the 2, or groups of 4. Okay, so if you think about it, it's really saying 2 times 3 times 2 times 4 will give me the total number of combinations. And that's what the multiplication principle is. Instead of using logic, instead of writing all this out, it takes long. It takes a long time to write it out. Jumper, jeans, jumper, shirt, jumper, jeans, with formal shoes, and then black socks. It takes too long, but the logic to it that we're teaching here is a quicker way of counting it. How many different ways, how many different options are you choosing each time, and you multiply them together. Okay, so in that quick example that I just did, would have been 2 times 3 times the 2 times the 4, and what's that? 6 times 8 is 48 different combinations, and that's much easier than writing it all down. Okay. Any questions there, though? Does that make sense? Yeah? All right. So, your turn. How many options are there? Sandra has 3 different skirts, 4 different tops, 5 different pairs of shoes. How many choices does she have for a complete outfit? 3 times 4 is 12. 12 times 5 is 60. There are 50 different combinations to it. Yeah? Okay, so that's a technique that we're learning to count. Instead of listing it out, I mean, that's the most preliminary skill that we can do. There has to be quicker ways, and that's our quicker way there to count. All right, so we've got, what was that again? That was 3 times 4 times 5. That gives me 60 different combinations that I can have. Okay? Let's try our next one. Now, we've learnt multiplication principle. We can now also talk about addition principle. An addition principle is when you want to choose 2 separate tasks. Okay, so here it says in some instances we have to count the number of ways of choosing between 2 alternative tasks. In this case, we use the addition principle. What does it mean? Let's do an example. Oops, not an example. Here we go. Let's say to travel from Melbourne to Sydney tomorrow, Cara has a choice between 3 different flights and 2 different trains. Okay, so how many choices does she have? So this is asking, well, she has a choice of a flight, and there are 3 different flights there, and 2 different trains. 2 different trains. Okay? So we think about it, she has 3 flights and 2 trains, but you're only going to choose 1 to go. Okay? So the question here, if you think about it, suppose there are m ways of performing one task and n ways of performing another task. If we cannot perform both tasks, that's the key part. If you can't perform both the tasks, then there are m plus n ways to perform one of the tasks. Okay? So in this question here, how many choices does she have then? Logically. How many choices does she have? 5. Okay, there's 3 for flying and there's 2 for train. So in total, how many choices does she have? 5. Okay, if you think about it in a tree diagram, I'm really just saying choices of getting from Melbourne to Sydney, you have 3 flights, flight 1, flight 2, flight 3, and train 1, train 2. So they're all separate. You can't do both tasks. You can only choose one of them. So for flying there, she has a choice between 3 and 2 different trains. Well, naturally, you can only choose flight 1, flight 2, flight 3, train 1, train 2. How many different choices do you have? 5. 3 plus 2. Okay. How do we feel about that? Does that make sense, the difference between the two? If I had said, if she was doing a connecting flight, she does a flight, she has a choice of flying first, and then choosing a train, or training first and then flying, then that would be different. That would be a multiplication. Okay, a multiplication principle. But I said you can fly and then train to get to Sydney. Then if there were 2 different trains and there are 3 different flights, then there'll be 6 different ways. And there'll be 6 different ways in that case. But in our case, we only had one choice: flying or training to get to Sydney. There's 5 in total. Okay. All right. Now, let's have a look at this one. This looks scary and whatnot, but really it's the same thing. There's no quick way but counting. Okay? Now, the counting is you're looking at how many branches there are. It's like a tree diagram just curved. Okay? So if you think about it, in your first go, you got 3 options. After the second option, you now have 1, 2, 3, 4, 5. There's 5 options over here. Okay? And then finally, in the next one, you got another 5, and you got another 2 to get to your destination. Or technically another 1. Right? The question says, how many paths are there from point A to point E traveling from left to right? Okay. So how do we calculate this? How many different ways are there? From A to E. From here to here. How many different ways are there? You have? How did you know it was 15? What did you do?
Two rows, like 2 times 3.
Yep.
6.
Yeah.
And 6 plus D to E is 7, and A to F 8, and there are 2 to H. 2 times 3 is 6, and 8 plus 6 is 14, and 14 plus H to E is 15.
Whoa. A lot of explanation there. I'm just trying to confirm. Because you can go there's like 1, 2, 3, 4. That's one combination.
Another way. Many ways, too many ways.
Yeah.
Okay, if you just go to the top one, 2, and then times the next 2, times the next 8, and then that's just 1, so it's still an 8.
Yeah.
And then the next one,
And that's so bad.
1 times 3 is 3,
And
times
that's
3 is 9, so it's different. That's
Use
9.
That's what I was thinking too. But I was trying to figure out Stella's layout. So that's what I was thinking. I'm thinking there are 2 branches. If I didn't have this one, if you think about it as a tree diagram, it'd be like saying, I have 2 options to get to B. After B, I now have another 2 option. I have another 1 option. So from here, that was 2 ways to get there. Another 2 ways, another 2 ways, and then that's 1. So in terms of different combinations, I can have A, B, C, D, E, that's 1, and you can have A, B, C, A, B, this way. But the point is you have 2 ways, 2 ways, 2 ways by 1 way. Total number of combinations, multiplication principle. That tells me I've got a total of 6 ways. And then on the bottom, it's the same thing. I've got 1 way with, for every 1 I have 3. For every 3 I have 3. And for every 3 I have 1. So it makes sense that if you do 1 times 3 times 3 times 1, that gives you 9, 8 on the top. So together it's 17. That's how I would have done it too. But what did you do, Scarlett, again? I'm trying to figure out what you were doing just now. You said
B, C, D. Is it 2, 2, 1? Is that what you said?
Just forget about it.
Oh yeah? It works. I mean, it seems like you were close. I think you were just missing something, that's all. So maths, remember, there's a lot of ways for solutions for maths. It doesn't have to be the way I just said. As long as you have a way that's consistent and you can work out all possible solutions. I don't care how you do it. You can list it all out if you want to. But that's how I would have done it. I would have done multiplication principle, and then addition principle. That's what I would have done. Okay?
Alrighty, let's go. Next one. What about this one now? Let's go with this one.
A bag contains 1 blue token, 2 red tokens, and 1 green token. So just think about it. 1 blue, 2 reds, 1 green. 3 tokens are removed from the bag and placed in a row. How many arrangements are possible?
Start drawing it if you want. So you got a bag. Got a bag. 1 blue, 2 red, 1 green. 3 tokens are removed from the bag, so that means you're choosing 3. Choosing 3 from the bag and placed in a row. So an example could be 1 blue, 1 red, 1 green. Another combination or arrangement I can have is 1 blue, 1 green, 1 red. I can also have 1 red, 1 red, 1 green.
How many different ways are there? You don't want to sit there and list every one of them. There has to be a quicker way. Just think.
Listing would take too long. I want you to figure out addition or multiplication principle.
What are we doing? The total number of ways we can have.
A hint to start off with is when you first draw your diagram, or tree diagram, my first go, what are my options? What colors can I have? Yeah, red, blue, green. So start off like that. Start off with, I can either get a red, blue, or green. Let's say I got a red. Then how many options do I have after choosing a red?
So if I took 1 red out,
I still have another 3. I still can get either blue, red, or green. So I can still have red, blue, or green. But let's say I chose my red. Let's say I had a red.
so if I said I would choose, this is my first go, second go, on my third go, I chose a red again, then how many options do I have after that? 2. It's either blue or G, or blue and green.
So if you write it out, it's blue or green, logically. But then if you chose B, then you can either have red or green. Or you can have red or blue.
This one. That's 1 times 3 times 2. For every 2, so 3 times 2 is 6 there. But then you have to work out these ones too.
Well, if you chose a blue,
So you said 3, the first one is 3. Multiplied by 3, the second one is 3. Multiplied by 2, the next one is 2. Multiplied by 1.
yeah. So there are 3 options here and there's 2 options there. So this is 1. So 1 times 3 times 2. Whereas blue, if you chose blue, you have a choice of 2 reds. Got a red, red, and a green. Or you can think of it as red or green.
Does this make sense what I'm doing here? I'm just saying if I chose blue for the first go, the next one I have red or green, that's my only 2 other colors. But if I chose the green, then I only have reds left. If I chose a red, I still only have a red left. I have red and green.
Red and green. There you go. And last one was green. If you chose green, you can have a blue or red. If you chose a red, you still have blue or red. And if you chose a blue, you only have a red. So in total, 1 times 3 times 2 plus 1 times 2 times 2. Oh, actually, that's not true. Yeah. That's 1 times 1 times. Oh, that's so ugly. Actually, it's 1, 2. There's 2 ways there. Two, 3. Total 12 ways. Is that all? Is that right?
Yeah, that's
I don't disagree.
Why would you get?
Why is it 12? Because aren't there 3 options in the first one? Red, blue, or green. And then 3 options, which makes 9. And then
2.
No, so 3.
Oh, this one.
Yeah, 3.
So you had, if you got a blue, then
We only get red.
red or green. But if you got red, you still have another red again. So you got red or green. That's 2 there. But the problem with this one is, if you got a green and you got a blue, the next one has to be a red. There is no red. Yeah. I'm just drawing it so you can do it. That's the only one that's tricky.
It's only when you have
It's going to be 3 times
Wait, are we confused by this? No?
Yes.
I'll go through this, but at the meantime, those who understand it, you can start on question 1 to 8 of exercise 7A. And 1 to 8. Yeah, 1 to 8.
Is that all the questions? Oh, I did a single question.
Sorry?
Don't worry.
Yes. Now, for those who are finding this confusing, I assume the top branch we understand. So, this was easy because it was consistent. For every 3, there were 2. So that makes sense. This was just 1 times 3 times 2 gave you 6. So that makes sense. The top one was easy. 1 times 3 times 2. For every 1 there's 3, for every 3 there's 2. The problem with the second one is it's not true. For every 1 there's 2, for every 2 there's 2. That's not true. See, if I colored it in green.
So yeah, but see that the reds, they're the same red, but they're both red, but they're 2 separate reds. So why don't we what if they be red? But they're 2 separate reds. They're 2 separate reds. What's the difference? Like they're 2 separate items.
It's a red.
Yeah, but they're 2 separate. Yeah, oh exactly. All red. No 2 things are the exact same.
In terms of combinations, you can have a red and a red though.
But which red are you having? Now we don't know. Yeah, exactly.
Or in that case, then you should have another red here.
Exactly.
If you were talking about red 1, red 2,
Yeah, exactly.
but we're talking about red ball.
But how do we know that?
They're both a red ball.
We're actually not talking about any balls, we're talking about tokens. Thank you very much.
Tokens. Yeah, red token and you don't. That's it. Red, green, and blue. There's no red 1 token. Okay? So there's 2 options at the end. If you think about 1 by 1 by 2, that's 2 options here. 1 by 1 by 1. That's the concept. Draw the tree home, have to figure it out. But otherwise, question 1 to 8, I'll leave this here just for you to work with. In the meantime, I'm going to pass out your sack. It's good work. Average, I think it was 73%, so not bad. Too easy, actually. Maybe I should have made it harder. Michael. Sava's not here. Oh, I should stop the video.